So lecture 26. So I just gave you a packet. It starts with 25. That was because the packet wasn't copied in time for class yesterday morning, so you have a redundant 25. So just flip to 26, inverse functions part 2. So we spent last class talking about inverse functions. What did we learn? What do you know about inverse functions now? Undo each other. What else? Yes, absolute value doesn't have an inverse function. Why not? How do you know? The horizontal line test. Good. What else? Let's undo each other. So yeah, that's kind of the round trip thing, the round trip idea. Plug X in, you get X back. Yeah, Julie? Yes. A function can't have two outputs for one input. Actually, let's say if a function has two outputs for one input, then it has no inverse. If a function has two outputs for one input, and it has no inverse function. Horizontal line test. What's the role of input and output in two inverse functions? They reverse. Inverse functions reverse the role of input and output. Now, other words that we use for input and output are X and Y, right? Or independent variable and dependent variable. So an inverse function changes the roles. Inputs become outputs and outputs become inputs in the inverse function. All right, so now that we have a good review, this is sort of a nice little summary of the things we talked about last class. So if f is a one-to-one function, that means it passes HLT and it has an inverse. Its inverse function, which remember we denoted this f, looks like f to the -1, but you read it f inverse. Its inverse function is defined by f inverse of y equals f equals x when f of x equals y. So in pictures, I have two machines. This will be f, and this will be f inverse. So in f, I could put in an x, and out comes a y. If I put that y into f inverse, out should come x. Just undoes whatever f did. So if f of x equals y, then f inverse of y equals x. So you can see the exchange of input and output roles. Okay, here, my input was x, my output was y, and here my input is y, and my output is x. All right, so let's take a look at a simple linear function, f of x equals 3x plus 4. What is f of 2? 10. That just means plug a 2 in for x, right? So f of 2 would be 3 times 2 plus 4, which is 10. All right, so what is f inverse of 10? 2. It's the round trip, right? F inverse of 10, f inverse is the function that undoes what f did. So if f took a 2 and made it into a 10, f inverse will take the 10 and make it into a 2. So that's one way. The fact that we already knew what f of 2 was made it possible to write this out real quickly. But let's say I want to find f inverse of 31. How do I figure it out? Yeah, because 31 is an input into f inverse, right? Which means it was an output for f. And we want to figure out what input created it. Okay, what input to f will give you a 31? So here's my formula for f. So I want to know what input, what x value, will give me an output of 31 in the function f. Does that make sense? Okay. So then I solve this equation, subtract 4 from both sides, and I get 27 equals 3x. So x is 9. So f inverse of 31 equals 9, and I know it's true because f of 9 gives me 31. So if I want to find the inverse function in general for any x, what do I do? I heard a couple of good ideas. Replace the y with the x, and then I heard undo the steps of what I did to x to figure out what x I started with. Okay, so I have an inverse function. We'll have f of x equals 3x plus 4. And I want to be able to figure out f inverse of any number, right? Like here I put in a 31. So I replaced the f of x, the output, with that 31. So basically I want to say if I put a number here for f of x, if I put some number y, then I have to solve for the input that would give me that y. Okay, so in the last example, that y was a 31, and then I solved for x. So in general, I'm just going to leave it as a y and solve for x. So I'm going to subtract 4 from both sides. And then I'm going to divide both sides by 3. So I get x is y minus 4 over 3. So that's the input that will give me a random y. And then because we're so used to, it's so ingrained in us that x's are inputs and y's are outputs, this looks a little weird, right? So when I write f inverse, I rename the y with an x and the x with a y. So this is going to be x minus 4 over 3. So f inverse of 31 would still be 31 minus 4 over 3, which is 9. And it kind of makes sense because inverse functions swap the role of input and output. So we should call the x's y's and the y's x's. So f inverse is just a function that undoes what f did. So f took x as an input and it multiplied by 3 and added 4. So f inverse is going to undo that, and it's going to subtract 4 and divide by 3. Right? To undo what was done to x, you undo in the reverse order of what was done. All right, so finding an inverse function algebraically. If a function is a one-to-one, then we can use algebra to find f inverse, and I'm going to write it out in sort of a step-by-step method. Although you don't have to memorize the steps because we just did it right here without knowing what the steps were, right? We found the inverse function without knowing the steps, but I'm going to do it out step by step so you have a procedure to follow if you like following a procedure. All right, so I'm gonna write out the steps and we're gonna do an example along with it. So step 1 is check that the function is one-to-one. How do you do that? Put in the calculator, and what am I looking for? Horizontal line test. Okay, so this is HLT. So let me pull up my calculator and take a look at the square root of x cubed minus 8. Okay, so the square root of x cubed minus 8. And I guess I'll just go with a standard window. I'm not really sure what a good window would be, so I start with this. And can't see that much. So there's nothing over in this left side, so I'm going to change the window so that it goes 0 to 10. And there was nothing negative in y either, so I'll go 0 to 10 there. That's better. Better. Does it look like it passes HLT? Yeah, passes HLT. So we graph and check HLT. Done. Okay, step 2 is we replace f of x with a y. So we're going to write y equals the square root of x cubed minus 8. So we're saying if f of x had some value, some number y, like in the previous example we had a 31. So I'm going to call that value generic unknown value y. Step 3 is going to interchange x and y, replace all the y's with x's and the x's with y's. And that's because that's what an inverse function does. It changes the role of input and output. So we're going to make the x's y's and the y's x's. So you get x equals the square root of y cubed minus 8. And step 4 is solve this new equation for y. So this is the undo part. This is the undo, the steps that are going to undo the original function f. So what do I do to solve for y here? What should I do first? Square both sides to get rid of this square root. So square, square. So on the left I have x squared. And on the right, my square root and my squared just cancel, and I have y cubed minus 8. Okay. So let's remember we're trying to solve for y, trying to get y by itself. So what should I do now? Add 8 to both sides. So I get x squared plus 8 equals y cubed. Now what? Cube root both sides. Great. To undo the cube, we take the cube root. So I end up with y equals the cube root of x squared plus 8. Step 5, replace the y with an f inverse of x. So I have, instead of y equals, f inverse of x equals the cube root of x squared plus 8. That's my inverse function. It undoes what f did. So let's go back and look at f and see what it did to x, right? The function f takes an x, you plug in an x, and it cubes it, subtracts 8, and square roots. So we have to undo what was done in the reverse order. So we should square, add 8, and cube root. That make sense? So the first thing that was done to x here is we cubed it, then we subtracted 8, then we square root. To undo, you square, add 8, cube root. Undo everything that was done in the reverse order that it was done in. So my last step, oh, this is one thing I forgot to put in our summary of things we learned last class. It's sort of included in the round trip. So let me go back to that first slide. When we wrote round trip, that means that when you apply the rule G and then the rule F, you get the X back. Or, and the other order works also, right? F of G of X gives you X back, and G of F of X gives you the X back. So when you plug in an X and you run it successively through both machines, it gives you the X back. So this is how we check our work to see if our inverse function is correct. I'm going to compose it with the original function and see if I get X back. So let's do F composed with F inverse of X. We'll do this one first. So I don't have a value for X. So what I do next is I'm going to replace F inverse of X with its formula. So this is going to be the cube root of X squared plus 8. So what I want to do now is apply rule F to this input. Okay. This cube root thing, I'm going to apply rule F to it. So F was the square root of x cubed minus 8, right? So this is going to be the square root. Instead of x cubed, it's going to be this input cubed. Square root of this formula cubed minus 8. So in the formula for f, this was the x, and I replaced it with this formula. So now let's just simplify this expression. Working from the inside out, what do you get when you take a cube root and you cube it? They cancel. So this is going to be the square root. This cube root and this cube cancel, so I have x squared plus 8 minus 8. What is plus 8 minus 8? Cancels. So I have the square root of x squared, which is x. Hooray! So now you try, in your groups, do the other direction. Compose f inverse with f of x. And if you're stuck, raise your hand. I'll come around and help you. And then the minus 8 and the plus 8 cancel. And I get the cube root of x cubed, which is x. So now we know that our two functions really do undo each other. That's why we now get to revel in a job well done. here's a quick way too. So let's say that you get a little lost in the algebraic manipulation here, which could happen, right? You end up saying that, yeah, you end up saying that if you plug an x in and you apply rule f and then rule f inverse, you get x back. So we can check it with a number too, rather than a generic x, because there's a lot of symbolic manipulation here, and it's easy to make a mistake. So we can also check it with a number. So I'm going to check f of f inverse of 2. Sure, let's check f of f inverse of 2. Shoot. Actually, I'll start a new slide. Okay, so f of x was the square root of x cubed plus 8 minus 8. And f inverse of x is the cube root of x squared plus 8. Yeah, okay. So let's just check f of f inverse of 2. So plug a 2 into f inverse, and what do you get? Yeah, so plug a 2 in here, I get 2 squared, which is 4, plus 8 is 12, and then cube root it. So I get the cube root of 12. Oops. So I'm going to replace the f inverse of 2 with the cube root of 12. So then I take f of the cube root of 12. So in my f formula, replace the x with the cube root of 12, and I get the square root of the cube root of 12 cubed minus 8. And what's the cube root of 12 cubed? 12. And so I have the square root of 12 minus 8, which is the square root of 4, which is 2. So I plugged in a 2. I got a 2 back. So that's exactly, this is what we did. We just did it with a generic x, and it just looks a little overwhelming sometimes. But to prove that two functions are inverses, you have to prove that the round trip happens for any number. So you can check it for one quickly and say, okay, I think I did it right because it works for this one number. But to prove that it works all the time, you have to do this symbolic thing with just the x. You have to be able to do this on a test, yeah. I could give you two functions, f and g, and say, are they inverses? And you would compose them and show that you get x. Yeah. Okay, so I'm going to have you try. Apply the procedure we did. It's like 6 or 7 steps. Find the inverse function of f of x equals 2x minus 5 cubed. Let's go through it together. So our step-by-step process. Step 1 was check that it passes HLT, right? So I should draw a quick sketch of the graph. Okay, so go to y equals. I'm going to type in 2x minus 5 cubed. Start with a standard window. That looks like it passes HLT. Okay, so good. We got that. HLT, check. 2 was replace f of x with a y. So we write y equals 2x minus 5 cubed. Step 3, make the x's y's and the y's x's, because that's what an inverse function does. It changes the role of input and output. So I'm going to make the y an x and the x a y. Step 4 is solve this new equation for y. These are the steps that undo what f did. When you solve this for y, you're undoing all of what f did. So what should I do first to try to get y by itself in that equation? Cube root both sides. Cube root both sides. To undo this cube, I'm going to cube root. So I've got the cube root of x. The cube root of something cubed just cancels, and I have 2y minus 5. So what do I do now to try to solve for y? Add 5 to both sides. So I get 2y equals the cube root of x plus 5. And then divide by 2. So I end up with y equals the cube root of x plus 5 over 2. Step 5 was replace y with an f inverse of x. And that's your answer. That is the inverse function. Step 6 is to check it. Okay, so we have to compose the f and f inverse to check it. Let's do it first with just a number. So this is sort of a check for to convince ourselves that we did it right, and then we'll go about doing the composition with the x to really prove that we did it, that we have the inverse. So let's do f of f inverse of 8. And I picked 8 because I know I can take the cube root of it. That way I don't have to deal with ugly numbers. So what is f inverse of 8? Using our formula for f inverse, if you plug in an 8, what do you get? 7 divided by 2, yeah. 3.5. Sorry, it's f of 3.5. So replace f inverse of 8 with a 3.5. And then what is f of 3.5? Scroll back up so I can look at the formula for f. If I plug a 3.5 in here, I get 2 times 3.5, which is 7, minus 5 is 2, and 2 cubed is 8. Okay, so I can be pretty confident that I did this right because I got a round trip when I did an 8. But let's do the final, official proof that we really have the inverse. So remember, f of x is 2x minus 5 cubed. F inverse of x is the cube root of x plus 5 over 2. So I have to show that when I compose them, when I plug one function into the other, I get x back. So let's do f of f inverse of x. So first step, replace f inverse with its formula. So this is going to be f of the cube root of x plus 5 over 2. So now what this is asking me to do is apply rule f to this input, right? So whatever I replace x with in the parentheses, I have to replace all the x's with in the formula. So if this said f of smiley face, it would be 2 times smiley face minus 5 cubed. But it's not a smiley face, it's this ugly formula thing, right? F inverse. So I'm going to replace this x with this formula. So I'm going to have 2 times the cube root of x plus 5 over 2, then minus 5, and all of that is going to be cubed. So instead of saying 2 times x minus 5 cubed, I have 2 times all this ugly stuff minus 5 cubed. Then we just have to simplify that and cross our fingers that we get x, right? So, well, I have 2 times some stuff divided by 2. What happens there? The 2's cancel. So I have the cube root of x plus 5 minus 5 cubed. Working in the parentheses, what's plus 5 minus 5? 0, those go away. So I have the cube root of x cubed, which is x. Got it. All right, you do the other direction. Do f inverse of f of x. You know you should come up with x. See if you can make it happen. We'll see. Okay, so f inverse of f of x. I'll do a new slide. Is that a plus or a minus? I can't remember. Plus. Okay, and then f of x was 2x minus 5 cubed. All right, so I did f of f inverse already. Now I'm going to do f inverse of f of x. Okay, so step 1, replace f of x with its formula. So this is going to be f inverse of 2x minus 5 cubed. So remember, whatever you replace in parentheses in the on the left, you have to whatever you replace that x with, you have to replace all the x's in the formula with it, right? So if this said f inverse of hearts and stars, right? This would be the cube root of hearts and stars plus 5 over 2, right? So in this case, I replaced the x with a 2x minus 5 cubed. So I have to replace this x with 2x minus 5 cubed. So instead of the cube root of a plain old x, I have the cube root of 2x minus 5 cubed. Then I still have the plus 5 and the over 2. Then we just have to simplify this thing and cross our fingers that x comes out, right? So when I have a cube root and a cube, what happens? They cancel. So my cube root and my cube cancel. So I just have 2x minus 5 plus 5 over 2. Minus 5 and the plus 5 cancel. 2x over 2 is x. So I know I'm right. All right, so moving on to a little bit different topic. We're going to sketch graphs of inverse functions. Now remember, inverse functions switch the role of input and output. They make x's y's and y's x's. So the coordinates of the ordered pairs on f inverse are the ordered pairs on f, but we switch the x and the y, right? So we can use the coordinates to create a graph of f inverse. So here's a graph of f right here. I want to sketch f inverse. So the way I do it is list a few nice points on the graph of f. So let's see, I'll pick a few nice points that cross grid lines. And so maybe I'll pick a couple over here too, just to have a few that are negative also. And that's good. So my coordinates of these points are, that looks like -2 1/4. And 0, 1. And then the next one looks like 1, 2. And this one looks like 2, 4. And the last one is 3, 8. 2, 4, and 3, 8. So the corresponding points on the graph of f inverse are just going to switch the x and the y, switch the input and the output. So I'm going to have 1/4, -2, 1, 0, 2, 1, 4, 2, and 8, 3. I'm going to plot those new points and connect them with a nice smooth curve. So let's see, 1/4, -2. 1/4, -2 is like right there. Oops. And then 1, 0, 2, 1, 4, 2, and 8, 3. So I have 4, 2, and 8, 3. I'm going to connect these with a nice smooth curve. And what do you notice about the green line I just drew in the original function f? Yeah, they're mirrors of each other, and the mirror is that diagonal line, which is the equation y = x. They're mirrors of each other over the line y = x. So the graph of a function and the graph of its inverse are symmetric about the line y = x. If you fold along that line, the two graphs would lie on top of each other. Okay, so let's take a little rewind to the ideas of domain and range. This is a plain old function, not talking about inverses yet. What's the domain of this function? Or how could I calculate the domain? Yeah, Dustin? 2? Is 2 the only value of x I can plug in there? Greater than 2. Okay, tell me how you got that. Right, okay, so whatever's under the radical, which in this case is x³ - 8, can't be negative, right? It has to be bigger than or equal to 0. And you just did this in your head. You didn't write this out. But you solve this inequality. So you add 8 to both sides, which means that x has to be bigger than or equal to 2. So that's my domain, 2 to infinity. All right, what about the range of that function? What kind of y values do I get as outputs when I take the square root of x³ - 8? Can I get 0 as an output? Is there an x value that will make y 0? 2. Yep. So 0 I can get as an output. Can I get, I don't know, 5? Can I get 5 as an output? Yeah, I can. Can I get -7 as an output? Why not? You can't get a negative when you take the square root of a number. The square root of a number is always positive. So my range, I can get by kind of thinking it through, and I would say I can only get positive numbers or 0 when I square root something. If you couldn't come up with that just by thinking about it, you could look at a graph. Because I know you know how to find domain and range from a graph because you did it on the last test. So let's take a quick look at the graph of the square root of x cubed minus 8. And when we looked at the graph of this thing earlier, because this was our example when we were finding an inverse function, we used 0 to 10 and 0 to 10. And we're supposed to give all the possible outputs, all the y values. So maybe I'll actually go like -2. So my y values start at 0 and get bigger. So for some reason, it's not drawing this last little bit, but it's there. So you can get it from the graph also. All right, so now we know the domain and the range of f. So what is the domain of f inverse? Where you 0 to infinity. Yeah, it's the range of f. The domain of f inverse would be the range of f. And what's the range of f inverse? The domain of f, 2 to infinity. Okay, domain and range switch. All right, so I have 3 graphs drawn in this picture. One is the line y equals x. One is the graph of f of x, the square root of x cubed minus 8. And one is the graph of f inverse of x. So label the 3. Which is which? All right, so one of these is easy to identify. The straight line is y equals x. Now, of the 2 remaining functions, which one has a domain from 2 to infinity and a range from 0 to infinity? The more vertical one. Sure, that's a good way to explain it. So this one is f of x. Its domain, its x's start at 2 and go forever, and its range starts at 0 and goes up forever. So that means that the other one has to be f inverse. And the formula we found for f inverse was, I don't remember. Go back, way back and find it. The cube root of x squared plus 8. Cube root of x squared plus 8. And so when I graph that, I get this picture. I get this parabolic or hyperbolic looking graph. Now, what do you notice about f inverse of x if I were to do, say, the horizontal line test? It wouldn't pass. F inverse of x wouldn't pass the horizontal line test. So in order to say in order for this graph to really be an inverse of f, I would have to get rid of this piece of the graph. And then I would also have the nice mirror images that I'm looking for. Okay, because f inverse, like you told me, its domain should be the range of f, 0 to infinity. So I should get rid of all the negative x's. So I would have to restrict the domain of f inverse to be 0 to infinity, which is the range of f. So I skipped, there was a small detail a few slides back that I was hoping none of you would notice and you didn't. And this is why I have to restrict the domain of f inverse. So if I go back to where I was doing the check, I did all this work to figure out what f inverse was. Right? I did all this work trying to figure out f inverse. And then when we were doing the check, we were composing right here. I said, what's the square root of x squared? And you all said x, and I went, great, let's move on. What is the square root of x squared really? The absolute value of x, yeah, or plus or minus x. The absolute value of x. So there was a small snag here, and that corresponds to the fact that we have to restrict the domain so that x can only be positive. Okay, so this is true if x is bigger than or equal to 0.